Hi, today I'd like to present our work on adaptive compliance shaping with human impedance estimation. Robotic exoskeletons have been widely used for assistance, teleoperation, and strength amplification. Our work focuses on amplification exoskeletons. The stability of strength amplification exoskeletons depends on the human impedance, including human stiffness and human damping, which appear in the most widely used mass spring damper human model. Humans are variable, and amplification exoskeletons can become unstable if designed with strong human impedance values. A conservative human model can provide strong coupled stability guarantees, however, restricts controller performance. For example, reference one emphasizes remaining robustly stable and uses system identification with the human in the loop to obtain a robust model of a single input, single output amplification plant. In this framework, it's clear how widening the uncertainty restricts the choice of crossover points and the closed-loop bandwidth. Thus, a more accurate estimation of human stiffness has the potential to improve bandwidth for both human-robot interaction controllers and amplification exoskeletons. We propose an amplification controller with online adaptive exoskeleton compliance, using a novel online human stiffness estimator based on surface electromyography sensors and stress sensors. This study contains two parts: the online stiffness estimation, including estimation diagram, perturbation experimental protocol, and random forest predictor prediction results, and the adaptive compliance shaping controller, taking advantage of the online stiffness estimation, including controller adaptation scheme and experiment validation. This picture shows our online stiffness estimation diagram. We use a random forest model to predict human joint stiffness, taking inputs of exoskeleton position theta and velocity theta dot, and signals from 2 stress sensors and 3 sEMG sensors. The prediction results are denoted by KH hat. This equation describes the human mass spring damper model, and stiffness KH is calculated using this model by least square fitting using data obtained from the perturbation method, and is used as the ground truth for the training of the random forest model. This picture shows the perturbation experiment setup to collect data and calculate ground truth stiffness KH. We use an exoskeleton that is force sensitive, single degree of freedom, series elastic actuated, and from Optronic Systems in Austin, Texas, to conduct the experiments. There is a force sensor around the cuff to measure the human exoskeleton contact force tau c, 3 sEMG sensors, and 2 stress sensors are attached on the arm of the subject. The subject holds a grip strength exercise device to modulate co-contraction in the muscles at the elbow. We held 2 experiment sets with and without human voluntary movement, respectively. During the experiments, signals from 3 sEMG sensors are amplified, rectified, integrated, filtered, and calibrated. Signals from 2 stress sensors are calibrated. Tau c, theta, and theta dot are filtered. Then they are recorded. In the experiment with human voluntary movement, there is a whiteboard in front of the subject with 2 lines. The subject needs to move the arm voluntarily from the bottom line to the upper line, indicated by the laser pointer attached to the end of the exoskeleton arm with a constant frequency. In both experiment sets, a perturbation signal with frequency F and amplitude A will be generated to move the human arm. In the second experiment set, the frequency of human voluntary movement is FV, which is 0.5 Hz. There are 11 experiments in each set. For each experiment, except for the perturbation signal, a bias force to change human stiffness will also be applied from 0 to 9.5 with a step of 0.5 Nm for the first experiment set and from 0 to 8 with a step of 2 Nm for the second experiment set. In addition, from experiment 1 to 11 in both sets, the subject will also hold a gripper with force increasing from 22 pounds to 82 pounds to generate muscle co-contractions. The parameter set is summarized in this table. With the perturbation experiments, we are able to collect and calculate the training data for the random forest model. 1/3 of the data are used for the testing, and the rest of them are used for the training. The prediction results are shown in this figure. The maximum error we got for the test set is 14.51 Newton-meter per radians, and the error variance is 3.01 Newton-meter square per radians square. Figure A shows the linearity between the ground truth stiffness KH and the predicted stiffness KH hat. The R factor is 0.993, which is pretty high. B and C shows one prediction example from experimental set 1 and 2, respectively. Now with the random forest predictor trend, we can apply this for the amplification controller. The relationship between exoskeleton position theta and the external torque can be expressed as equation 1, where ME is the exoskeleton inertia, tau E is the environmental torque, tau C is the contact torque, and tau F is the actuator torque. We implement a complex shaping amplification controller as tau F equals to alpha minus 1 times tau C, so as to achieve the nominal behavior in equation 2, where the human is amplified by a factor of alpha. Alpha is designed to be equation 3, with 2 pairs of conjugate zeros and 2 pairs of conjugate poles. We place omega Z2 at 10 Hz to avoid exceeding the bandwidth of the low-level fourth controller, and we have alpha SS defined as the steady-state amplification rate. Lambda 1 and lambda 2 are 2 tuning parameters. KH hat is the predicted stiffness. From those equations, we can see that the predicted stiffness is utilized to adjust the positions of zeros and poles. Without stiffness estimation, since humans are variable, the robust controller must be designed based on the most conservative bound of human impedance. Otherwise, the amplification exoskeleton may lose stability, and this limits the positions of zeros and poles, making the robust controller slow with limited bandwidth, as shown in this conceptual body plot. The brown line is the exoskeleton compliance, and the other 3 lines are the human side exoskeleton compliance. The distance between the brown line and the other 3 lines indicates the amplification performance. 2 blue lines represent the human side exoskeleton compliance of the adaptive controller, with high stiffness and low stiffness, respectively, while the red line represents the robust controller, designed with the most conservative bound of human stiffness. We can see there is an apparent performance improvement of the adaptive controller compared with the robust controller. To validate this performance improvement, we designed 2 experiments using the setup in this picture. The left picture shows the setup of the bandwidth test, and the right picture shows the setup of the stability test. In both experiments, there is a 2.5 pounds weight attached to the end of the exoskeleton, and the human is holding a gripper to produce different stiffness. For the bandwidth test, the rope is in place to maintain a constant position for us to see the steady-state response of the controller. For the stability test, a spring is attached to the end of the exoskeleton. When the experiment starts, we suddenly remove the spring to generate an impulse input. The rope is to limit the range of position to protect the actuator. The bandwidth test results are shown in this figure. The left 2 plots show the results with high human stiffness, and the right 2 shows that of low human stiffness. The upper 2 plots show the response of the adaptive controller, and the lower 2 show that of the robust controller. Tau A is the actuator torque, and the tau A equals to minus alpha SS times tau C is the amplification torque we want to achieve, where tau C is the contact force. It's easy to notice the adaptive controller responds faster in both cases compared to a robust controller. This proves the performance improvement in bandwidth. This figure shows the stability test results. The left one is obtained with high human stiffness, and the right one is obtained with low human stiffness. The orange dotted line shows the exoskeleton position change with the robust controller after we remove the spring, while the blue line shows that of the adaptive controller. We can see the position variance of the adaptive controller is smaller than that of the robust controller. And both controllers can maintain stability. As we mentioned previously, amplification exoskeletons can be unstable when the human stiffness is designed based on its wrong. We can make controllers faster, but they only work when the human applies the right stiffness. We conduct a test to validate this. We design the controller with a fixed highest human stiffness value, and then we conduct the stability test. The y-axis of this plot is the exoskeleton position. When the subject lifted his arm with a relatively low stiffness, the exoskeleton started to vibrate and lost the stability. When the subject contracted his muscle by squeezing the gripper, the exoskeleton stabilized. After he relaxed, the exoskeleton became unstable again. The controller goes unstable right here and here, when the human wasn't being stiff enough. This experiment highlights the importance of accurate stiffness estimation to our adaptive controller. The red dotted line at the top of the graph is the maximum position limited by the rule shown previously. In summary, we propose the adaptive controller using the stiffness estimation, which provides higher bandwidth than comparable robust controller design based on a conservative bound of human stiffness. Our random forest predictor was actually better than all of the published stiffness estimator we found, and it let us use the fast controllers without going unstable. For now, the predictor is trained for the data from one subject. Experiments with more subjects could be done to train a more general random forest model applicable to multi-subjects. A future work could be the integration of a backup safety controller, as proposed in reference 2, to take over if the learning system fails. Such a backup controller could offer firm safety guarantees, but would not interfere with the controller if it was not misbehaving. That's all. Thank you.